Good morning. Today we study about drift current and diffusion current in a semiconductor. Okay. We already studied about the classical free electron theory. In classical free electron theory, we observed that the electrons are moved in random direction in a metal space. Here, when they move in random direction, it collides with the electron and other ions. Due to this collision, whatever the velocity of the particles will be in random, and it has a random velocity also. V is equal to root over 3 kT by m. We already derived that equation. Now, if an external electric field applied to that material, that semiconductor or that metal piece, then the electrons will be accelerated opposite to the applied field. Accelerated opposite to the applied field. That electron moves in the opposite direction to the applied field. That motion is known as the drift velocity, and the flow of electrons is known as drift current. Here we study about this a small derivation, means we study about the drift current, means the current density of the drift current. So here, in next slide, we observe from this diagram where this is the positive charge, when we apply this in this direction electric field, the electrons will be moved opposite to this applied field. This is known as the drift current. Now, I want to derive a small derivation for the drift current. See here, we have to find out the current density. The current density can be written as J. For Jn is known as the current density for n-type semiconductor. So what is meant by current density? Here just briefly I will explain here. The current density is nothing but current per area. So what is meant by current? Current is nothing but I is equal to charge per time. Current is nothing but charge per time. So current density is nothing but J is equal to charge per time into area. Okay. If you multiply and divided with displacement D, okay, then it is equal to charge per volume, the area into displacement, nothing but volume, into displacement per time. Here the displacement time is nothing but velocity. Here it is known as the drift velocity. So finally we get E by V. Let's consider N. N is the number of particles per volume into E into D by T. D by T is nothing but drift velocity denoted by Vd. So finally the current density, drift current density is equal to N E V D, where N is the concentration of the charged particle per volume, E is the electron, and Vd is the drift velocity. But we know that the drift velocity Vd is equal to mobility into electric field, where mu n is the mobility of n-type semiconductor, electrons, mobility of electrons. For n-type semiconductor, we can written as mu n. So finally, the drift current density for n-type semiconductor N is equal to N G, instead of Vd means drift velocity, we can write it as mu n into E. Let the equation 1. This mu Jn represents the current density, the drift current density for n-type semiconductor. Then E indicates the electrons and then the concentration of electrons per a volume. Mu n is known as the mobility. E is the applied electric field. And this mobility also known as the coefficient of drift current. Mobility also known as the coefficient of drift current. Similarly, for p-type semiconductor, Jn is equal to, instead of, see here we have simply write P. P is for p-type semiconductor and E mu P and E. Let the equation number 2. Sorry, here we have to write J instead of Jn, we have to write here Jp. Jp indicates the drift current density for p-type semiconductor. So the total drift current density is given by J total is equal to Jn plus Jp. Okay. So total we get J total is equal to J total is equal to N E mu E plus P E mu P into L. This represents total drift current in a semiconductor. Similarly, we go for the another current density. That is nothing but diffusion current. Okay. See here, before going the diffusion current, in physics, we have studied about the fundamental laws. The wind can blow from high pressure area to low pressure area. Wind can blow from high pressure to low pressure area. Similarly, the water can flow from high area to low area. Similarly, the electrons also flow from high concentration region to low concentration region in non-uniform condition. It is in non-uniform condition. See here the definition is given. In non-uniform distribution of charge carriers, the charge carriers move from high concentration region to low concentration region. This process, this phenomena is known as diffusion current. Means here without any applying any external field, due to this unbalancing of this condition, distribution of unbalance of the condition of these electrons or charge carriers, the current will be flow from high concentration region to low concentration region. This is nothing but diffusion current. Here also we have to find out the current density for diffusion. Diffusion current. Here if you consider, here given the delta n or dn, where n is the concentration of the electrons or charged particles, where x is the displacement. It will be displaced up to the concentration will be displaced up to a certain x, then they became uniform. Then from this constant, this point to this point, the electrons will move from this point to this point, and here becomes uniform. Here it gives that the rate of flow of charge carrier to a unit area, that is nothing but diffusion current density, is directly proportional to charge, the product of charge, and the negative direction of concentration gradient. Negative direction of concentration gradient. See, I will show the simple derivation here. Here, the diffusion current density here is given from this definition. J n diffusion is directly proportional to negative direction of charge into dn by dx. This dn by dx is nothing but concentration gradient. The dn by dx is nothing but the concentration gradient. Now, Jn is equal to dn into electric field means here electron is in negative direction, and this is electron means, so it becomes the positive here. Charge into dn by dx. I will explain again this sign. Okay. So this is the diffusion current density. Similarly, for p-type semiconductor, Jp is equal to here the minus dp into E dn by dx. Here from this definition, we can written as the diffusion current density is directly proportional to negative direction of concentration gradient. So here the negative direction is minus dn by dx, and it is multiplied with electron, the charge particle of minus E. So minus and minus becomes positive, so we get here positive. Whereas for p-type semiconductor, minus dn by dx into E, so we get here negative. So the total current density is nothing but J total is equal to Jn plus J. This is the diffusion current.